Maybe some of you can join from that side. Huh? There's some seats on that side. Yeah. Yeah. You can join from that side. Huh? There's more seats on the other side. Yeah. You can go in. Yeah. Okay. Good. I think you can join from that side. If there's a bit more space there. But of course, in your case, you can sit in front. Right. Okay, I think we are nearly complete. So good morning to all of you. I'm Gautam Ram. I'm an assistant professor at the Delft University of Technology, and my specialization is the area of electric vehicles. So the session that we have today is going to be about the electric vehicles and the grid, from problem to opportunity. Maybe if you have some silence, maybe it helps out. We have a fantastic lineup of speakers that will cover different aspects of electric mobility. So we will look at power electronics technology, we will look at artificial intelligence, we will look at vehicle to grid, we will look at the human aspects of electric vehicle charging, and also look at wireless charging. Before we dive into the session and introduce the speakers, I have 3 questions for the audience, and I have 3 insights to give to you. So the first question, since all of us are here looking for a better tomorrow, can you give me a number which represents the total carbon dioxide emissions, including conversion from methane and NOx, that we as human beings emit, totally? Maybe one number. That's the problem we are targeting, right? First, we need to know what the problem is and how big it is. So one number from the audience. OK, I'll give you this number. It's about 50 billion tons of CO2. Huh? That's the problem that we are targeting today, right? We want to bring that to 0 and probably even remove more of that out of the atmosphere. Second question, how much of all those emissions is because of mobility? What percentage of, so we have the big pie, 50 billion tons. How much of that is just mobility? 40%. Another estimate? 20%. OK, so we have a range between 20 to 40. And since of all the emissions, most of us try to shame people who take a flight, how much do flying contribute to all of these transport emissions? Huh? We have the big pie, the small pie, which is mobility. Among mobility, how bad are planes? All the flying, private jets, public, I don't know, the 320s, 777s. 2% of only transportation. 10%. Any other numbers? 5. OK. So let's play a game and see how well we are within the audience. So I already gave you the answer. The total emissions, the 50 billion tons. OK, I mean, some estimates might be 52, 53, depends on whether you use land use change. About 17% of the emissions, sometimes it's 16, sometimes it's 18, is actually mobility. And if you see the split of within mobility, you see all of aviation is about 10% of our mobility emissions, right? And all of shipping is about 10%. So in other words, if you took a flight to here, you're contributing to the 10%. But if you took a car to this location, you're actually contributing to the 46%. So cars are a very big problem that we will have to deal with. Aviation is small also because the number of people who fly is also quite small, and because of those factors. Another interesting number here is heavy-duty vehicles. The number of those vehicles is very small, but the emissions is actually about 25% of this. So you have few vehicles which cause large emissions. You have a lot of vehicles which represent the cars. And the nice thing on the top are buses and trains, which are really small, right? So what's the message I want all of you to think about? The first message, rightly we are here in the Netherlands, biking is a fantastic way because, interestingly, biking was not there in that chart because it has no emissions, right? So biking, while it seems so obvious in the Netherlands for short distance to go on a bike, if I travel around the world, it is not so obvious. Why are we not taking the bike for our short distance commute? Rail is just 1% of all our emissions, which means for short distances, we shouldn't be taking the train more. So that's message number one. Message number two is, while we are talking so much about electric mobility, we should not forget the emissions we are producing from our electricity grid. So in this picture, I'm calculating how many grams of CO2 we produce for a kilowatt hour of electricity. And this is EU, on the other side is the G20 nations. And you see this big widespread number. You're looking at something like 0 in Iceland, to about 720 in Poland, and if you look at some G20 nations, you have about 750 to 800. If you look at an electric car, 1 kilowatt hour produces about 6 kilometers of range you can drive. So if you divide this by 6, you try to get a feeling of how much emissions we have at the power plant by driving an electric car. So the number is not yet 0. So the message for us is, no, I'm not telling you go drive the combustion car. I'm telling you go for the electric, but also keep in mind the emissions of the power plant, and let's try our best to become Iceland and Sweden and France, right? Bring those emissions down. And the third message, as we move to electric mobility, we have to remember there are 3 very important factors to move to electric mobility. The first is we need to build a fast charging infrastructure on the highways, right? If I don't have a fast charging infrastructure on highways, people are less reluctant because of range anxiety and the high purchase price of vehicles to go to electric vehicles. We have to significantly decarbonize the grid, and we have to ensure the purchase price of vehicles comes to an affordable price point. We are talking about $25,000 here in Europe. For a country like India, it needs to be at $10,000, $12,000, where I come from. So in the meantime, if you think we cannot decarbonize the grid, build a fast charging infrastructure, bring the price down, in the next decade, we should not be continuing to drive combustion vehicles for the next decade. We should seriously consider hybrids. In this picture, I've shown a Honda Civic, a Toyota Prius, a Chevrolet Volt, which is a plug-in hybrid, and a Tesla Model 3. And you can see the miles that you can drive with the energy in a gallon of gasoline, so which means it's 33.7 kilowatt hours. If I have that much energy in a gasoline or in a battery, how many miles I can drive? And you can see it goes all the way from 33 miles all the way up to 130 miles. And you see a sweet spot here with plug-in hybrids, that you can still get 106 miles per gallon when you're using the battery, and in a normal hybrid like a Prius, you can go 52. So in other words, just by moving to hybrids, in the short term, we can reduce our emissions anywhere between 1.5 to 4 or 5 times effectively. So let's not forget hybrids. If you can move to electric tomorrow, let's do it. But if you have to wait 10 years, let's not continue to burn gasoline in our cars. Okay? With that message, I would like to start this session. The first speaker we have for the session is Sebastian Rivera. Sebastian is a assistant professor of power electronics for DC systems here at Delft University of Technology. His research focuses on DC distribution, EV charging infrastructure, and high-power modular converters. His talk will be on power electronics for energy hubs for EV charging. Sebastian, the floor is yours.
Thank you. Thank you for that welcome, and it's a pleasure to be here. So, as you may know, my name is Sebastian, and I'll be talking about the power electronics on energy hubs for charging, but from the whole pile that Gotham just showed, I will be focusing on a rather urgent matter, which is the heavy-duty sector, like big trucks, long-haul trucks, and stuff like that, and how we are trying to develop new solutions into that direction from the power processing aspect, okay? So, the outline of my presentation, I'll be discussing a bit the particularities of the heavy-duty charging, like to know the load that we are facing, what are the regimens, what they look like, and why they are so different from conventional or light-duty vehicles. Then we'll pass on energy hubs, like why these multi-carrier, multi-physics energy systems can unlock solutions for implementing this in a larger scale and try to meet with the sustainable goals. And finally, I will discuss a bit of the challenges that we are trying to face locally and the ongoing research within the group and also within my students. And of course, I will send you some outlook and conclusions by the end of the presentation. Okay, so first, why is so different charging a heavy-duty vehicle? If you see here, I think this is oh yeah, I have a pointer. This is like a generalized map of all the charging solutions, starting on the left-hand side, the AC solutions like how will I charge my car just as I charge my computer or my cell phone. And as we move into the right side of the graph, we will, of course, increase the power. And when we change from the orange to the blue, it means that the power is entering into the car AC in the orange bars, and then we go up to the blue part where basically we're doing DC charging. Okay, why? Oh, sorry about that. Why is this so different? Like, we are trying to, this is where we currently standing, like state of the art chargers are about 600 kilowatts able to deliver the car, despite there's no an actual car that can sustain that much power. And we are trying to solve the problem of heavy-duty vehicles, which, according to several stakeholders and the design of such a system, we should be pointing at least to 1 megawatt charging rate in order to cope with both. Enable the drivers to rest for 45 minutes, which is by law. So every 4.5 hours of driving, the driver must stop for at least 45 minutes. And considering the recent developments of e-trucks, for a 4-ton truck, you are looking at something in the range of 600 kilowatt hour per battery. If you crunch the numbers, you'll get that you need, ideally, 800 kilowatts just to recharge that much energy in that time. But yeah, you have losses, you have old batteries, you have loose cables and stuff like that. So they reach to this consensus of 1 megawatt. And that's what they're currently doing. They are developing, truck manufacturers, electric companies, governments. They are working on this so-called megawatt charging system, which is looking for powers within 1 to up to 3.7 megawatts of charging. If you think about like a conventional highway station, probably the peak power designed for that 20 charging stalls might be within 1 megawatt. Now you have 1 megawatt per charger at least, and you can get at crazy rates as 4 megawatts. So yeah, the problem is huge. And if we consider we live in a pretty densely populated zone and our electric grid is already at capacity, like putting this on top of those shoulders might not work as good as we are used to, right? So yeah, I will talk about the power conversion because despite we might see energy systems with multi-carrier, multiple energy carriers, electricity will remain the dominant part. So, and in order to shape the power from our grid, which is AC, into the batteries, which are DC, you need to use several power processors or power electronic stages. From a structure point of view, the conventional solution is just to, of course, connect into the medium voltage because it's easier and you get less requirements from a grid operator point of view, and you can actually deliver or distribute the power into these charging stalls by using an AC approach. I have a big transformer, and then by isolating with smaller transformers, I can enable isolated charging ports. I can also do that in DC range. So basically, I have the main transformer that creates the local 480 volts. And then by using medium voltage isolated DC to DC stages, you can get the isolation that is required by standard to charge the vehicles. And then a more modern and more, I would say, less conservative solution is to use the solid state or the smart transformer approach, which basically you have a fancy power electronics converter acting into the grid with a lot of capabilities in terms of bidirectional power handling and a better performance in terms of THD, and then you will enable, again, isolated charging ports. Considering the amount of energy, this has proven to be, or it's showing to be the correct way to do it, so I will focus into this area. So I will be talking about designing novel power converters within an SST architecture, and at the moment we are working on the DC to DC stages, which is also challenging because we have larger powers. So what's the purpose of this slide? you can say, okay, let's just do whatever ABB is doing and repeat it, reach megawatt, reach whatever power you need. And if you see modern chargers, you see that they're comprised in such a way, like you repeat the same power processing block and you make these Lego-looking things. I want to reach certain power, I put more modules. I want to reduce the power, I take modules. But considering that you are thinking in the range of 300 to 600 kilowatts, the structures, sorry, why this keeps changing? The size of that module is in the 20 to 50 kilowatts. Take that and think about a 10 megawatt charger, a 40 megawatt charger. It's nonsense. You can get issues. Of course, modular is the way because that I just do one thing and I just repeat it. That can be beneficial from an economic point of view, but you need to increase the discretization size. It doesn't make sense to have such a small component. So if you have a larger power processing block, you get challenges because, okay, mechanically this might be hard to connect. The transformer, again, becomes the bottleneck because it's hard to design a light, efficient, and high-frequency transformer, like medium-frequency transformer, like within the kilohertz range. So yeah, and considering the power would be in the 10 megawatt, we are thinking of increasing the discretization size of the power stage. And yeah, just to show like the biggest demonstrator up to date is a 1.2 megawatt charging port that it was developed by NREL and working with Delta, and they just make the SST and design it 300 kilowatts power processing block. So that's the kind of thing that we're aiming. Okay, is it possible to create a power electronics building block in the 500 kilowatts range with high frequency isolation? It's challenging, but yeah, that's what we will try to do. So as I mentioned, we have a problem in terms of discretization of the power for creating such chargers. We also, as I mentioned earlier, will put a tremendous stress on the grid. We cannot just think, okay, the grid will deliver, because it's such a high scale that it will be catastrophic, I would think. And also we have particular challenges within the region, like it's pretty populated, the grid capacity, it's as it's up. And on top of that, we have two corridors passing in a pretty particular, there's a keynote of two 10T corridors in the Netherlands. And also Netherlands is enforcing a zero emission for logistic vehicles starting from 2025. So yeah, we should start creating these megawatt charging ports to supply or to provide logistic chains in order to continue the economic development of the country. And we have to do it pretty quick. So yeah, a lot of challenges. Why energy hubs? Why in the context of energy hubs should we create such energy systems? Like, if we think about decarbonizing the whole transportation sector, it doesn't make sense. Like, you cannot just rely on batteries, you cannot just rely on hydrogen, you cannot just rely on synthetic fuels, so you have to make commitments. So eventually we will deal with such a structure where basically you have different energy carriers. In this slide, I'm just showing liquid synthetic fuels, hydrogen, and electrons. They can be used to power different sectors of the transportation, depending on, of course, the regime, the size, and stuff like that. Why is relevant for me? Because you need to manage, at the end time, you need to manage electrons, and of course, electrons are handled or are driven by power electronics. So in every stage of this future, like zero emission sector, you will have power electronics, and given the constraints of like available energy, you need to focus on stuff like efficiency and compactness and reliability and redundancy and stuff like that. So it's a good place to start like optimizing power electronics. So what we are thinking, or what this energy hub concept might think, just think about three carriers for the moment. Hydrogen, which is a big thing right now, electricity, of course, and then we have thermal, or you add a thermal channel into your system. So you get the electrons, you manage them with power electronics, and you create an electron path to serve different processes. You have EV charging, but you also have the railway system. The railway system in the Netherlands is trying to expand, but of course it's hitting the wall of there's not enough electricity. And also you can power with the same concept industry processes like the chemical industry, hopefully the steel industry, and try to electrify the whole thing. Okay, so it can be done in order to seamlessly integrate into the grid, bring more sustainable energy, try to reduce the weight on the shoulders of the grid, and create these self-sufficient, at least temporarily, energy islands that will be heavily relying on storing energy. Different ways, different paths, depending on the case. I'm not saying that one kind of energy is better than the other, but we have options, we should play with them, and we will try to do as so. For the time's sake, I will skip this part and I will go to my ongoing research projects because I don't want to be the one that delayed the whole thing. So, first challenge is creating this power electronic building block within the 100 to 300 kilowatts by tackling a pretty difficult theme. It's like having a multi-port structure that is able to transfer power from one side to the other efficiently, compactly, and reliably. So with one of my students, we are proposing we're studying this problem, which if you try to optimize it, you will soon realize that, oh, this is non-convex. It's hard to optimize, so it's pretty computational expensive to try to do like the brute force and try to optimize and crunch the numbers. So we're trying to play around with the operation of the converter, try to eliminate some of the harmonics present, because basically that's the problem. You have power transfer at every harmonic in this square wave system. And on the other side, we're trying to play around with novel structures for the magnetic structure, sorry for repeating, in order to provide an efficient and simple energy path for the electrons to be flown from one part to the other. And also, if we have a good, nice, compact design of the transformer, we can easily use this multi-port structure to create a path for other carriers, such as electrolysis for hydrogen or integrating fuel cells. Oh, yeah, sorry. And the same idea, we're trying to see beyond the megawatt charging system, which is basically what happens after 4 megawatts for even larger vehicles. So we are, again, trying to create a power electronic building block for a total of 40 megawatt, a systematic assessment studying both inductive and conductive solutions. And we're creating a 100 kilowatt demonstrator to show our capabilities. And finally, the same idea, energy hubs for supporting the plans of NS and ProRail to expand the train fleet and provide new solutions and a better, efficient way of feeding the already pretty light emitting electric rail system. So yeah, we have a lot of challenges to reaching the megawatt level. The grid integration can be a stress to the grid, but if we add more carriers into the system, we can actually provide a solution that does not only reduce the power consumption, also can provide additional functionality. And EV charging, this is a pretty important thing, like HD heavy-duty charging can be a great showcase to show how DC distribution at different levels can be beneficial for the future electric grid. So thanks a lot, and if you have a question.
Thank you, Sebastian, for your speech. We know now that for the 25% of the heavy-duty emissions, we literally have a megawatt-sized problem to be solved. So right after all the talks, we have a panel with all the speakers. So that time you can keep your questions and we can discuss that together with all the speakers. The next speaker that we have is Gert. Gert is a full professor of Internet of Things at the Faculty of Industrial Design Engineering. His talk today will be on EV charging, human aspects, and responsible AI. Gert, the floor is yours.
Right. Thank you for having me today. Thank you also for the talk before me, because that you understand all the technical complexity. Now I want to switch the perspective to people. How many of you are looking at energy infrastructures from a people perspective? Hands up. All right, more than I expected, but certainly not the majority. So I want to delve into algorithmic transparency. And in particular, I want to tell the story of the transparent charging station. The transparent charging station is a speculative design project. It started as a speculative design project that turned into a very effective research instrument. Now, what is the transparent charging station? It is a mock-up. It is a non-functional prototype. It is a talking piece, which you can see here. It is basically a physical prototype of a charging station with 3 ports, and it has a very nice display, and the display reflects the charging decisions. So the assumption is there is an algorithm behind that that makes decisions based on contextual parameters, energy availability, and then routes energy to cars in a particular way. And the display is there so that people understand what is going on. Now, if you play or played Tetris, you might recognize sort of the underlying idea of the interface. It basically goes down and it shows sort of in different colors the distribution. But never mind, that's not the point. The problem, of course, and what is the motivation of this project? The problem, of course, is we don't have enough electricity at the right time, at the right point. And so we might have to make decisions of who gets energy, a little bit less energy, who gets more energy. Now, how do people react to that? How do we feel when we are driving up to our charging station and the charging station tells us, sorry, can't do. Yesterday I could, today I couldn't, I can't. So understanding the issues of having a smart algorithm in the charging station that makes decisions of a very contextual nature. And of course we have the complexity of the algorithm can be anything. We can sort of just figure in the availability of the electricity. We can look at aspects of the car. A car with a big battery, with a small battery, the typical driving behavior of a car. It's all technically possible. Do we want that? What's the reaction? And that the transparent charging station is an instrument to understand these issues, to help us have a dialogue with people around these issues. It is not intended as that's how it's going to be, let's test it, but let's ask a question. That was the intelligent side. What about the inclusive side, inclusive energy system, the human side, the societal side? I talked about the human experience. Metaphorically, we're lining up in front of the EG charging station, and the charging behavior might be completely unpredictable. Today, different from yesterday. We have a mental model. We go to a charging station, we have sort of a mental model. It's going to take that long, and everything will be fine. Now, that might, with an algorithm, that might not be the case. You don't get your fill. You might get annoyed. You might drive up with a very small, efficient car, and then comes a guy with a big BMW, and all of a sudden, he or she gets more, even though he came later. Now, there might be a reason in the decision logic to do that. Maybe the parameters have changed, But from a human perspective, that might look a little bit odd. And there might also be systematic biases. Well, all people with bigger cars are systematically advantaged, not necessarily because the algorithm is designed to do that, but it is the emerging behavior. Now, for example, Amsterdam has values, identified values, which they would like to embed into the digital infrastructure. And you can see them here. One of them is transparency, openness and transparency. We'd like to understand what is going on collectively and individually. And the transparent charging station allowed us to start investigating that. So we had 2 rounds of investigations. One is using this prototype, which was designed by a design firm, connection with several energy companies, the Responsible Sensing Lab in Amsterdam. And we held workshops to understand what are the reactions, what's the decision logic, what is the reaction to different decision logics. People came up with the idea of having priority cards, a medical doctor getting always priority. So there are lots of possibilities in how such a thing could be designed. Now from that, we informed an empirical study. We said, okay, let's get a little bit more serious. Let's do a study, let's build a prototype, let's take it to people, and more closely investigate the reaction of people to that. And you see the transparency, the explanation of the charging behavior is a little bit more complex, looks a little bit more traditional. And again, we didn't build a fully functional system. We built basically a box with an iPad, but we took it to a real charging station. And when people charged their cars, we approached people and said, hey, we're investigating this. Here is the interface. So people were in the situation, and they could better reflect on the experience that such a charging station might create. Now, what did we learn? The first interesting thing was the discrepancy between what the experts thought transparency does. Transparency is good. We tell you what it does. You be happy. Done. And what people told us, well, you give me explanations and facts. I can't do anything about it. What's that about? You tell me how the algorithm nudges me or gives me electricity or not. Why are you telling me anything when I can't do anything about it? I can't influence the system. So that was a negative reaction to some extent. And so there was a real clash between the ideas the official system, the experts, the city, the technicians had when designing transparency, something good, into a system, and some of the reactions of people. More specifically, we found not a uniform opinion about these things, but some people said, well, I don't really care, leave me alone. Others said, oh, that's too much, I don't want to deal with that. Cognitive overload, leave me alone. Another said, no, now I'm annoyed because you tell me that you're manipulating me, but you don't give me any input. In particular, the concern of algorithmic anxiety, which is well recognized for Uber drivers or Airbnb hosts, actually shows up all of a sudden here in the street by simply charging your car, because you're trying to understand, what is the algorithm doing? What do I need to do in order to trick the algorithm to give me the electricity which I want? And that is not necessarily the experience which we would expect and hope for. All right. Transparency, great idea, mixed results. The idea of enhancing the street-level experience during charging maybe is not the right approach. It's the wrong level of transparency. And so we changed tack a little bit in our research from the street level experience to the collective, to the more societal aspects. And we looked at a broader set of possible objections people have to the existence of algorithms in their electrical infrastructure. From the very existence of such a smart charging solution. No, we shouldn't be doing that. It should be dumb so that I can understand it. To what should the policy be? Is that the right policy? Who gets priority? Who doesn't get priority? To the objection with respect to a faulty outcome. I charged a shared car, but for some reason I should have gotten a certain amount of energy, but I didn't. And so on. So there is a larger set of concerns. It's to some extent it's on the policy level. And that is the interesting aspect because all right, I'm going in the wrong direction here. All right. Because intelligent algorithms, they do not only embed policy, they make policy. By developers developing a particular form of intelligent algorithm that behaves in a particular way, that shows a behavior, emerging behavior to some extent, it all of a sudden turns into official policy. That's how we do things. Even though there might not be anyone who actually designed the outcomes and controls the outcome. And that is very interesting. So we developed a framework to understand the whole system. And the control points to open up the system so that we as society collectively can contest certain design decisions of how the whole system is designed and how decisions are actually being made by the whole system. And so we have here, here's the AI system, so the algorithm. We have the decision subject, that is us standing in front of the charging station, system developer or operator, the human controller, for example, privacy regulator, privacy officer, and so on. And we identified the connection points. Here's an automated decision. Now, and we looked at transparency, we looked in what is here indicated explanation. That was the point which we looked at with the charging station before. But the point is we identified more leverage points which we need to design. We need to look at how can we create these connections between the different stakeholders and what do we need to do so that we collectively can contest the system or the outcomes. You can see I'm moved a little bit back and forth between the slides. I hope you don't mind. And a little bit more into details what these intervention points are. However, this is a story for another time. Don't have time to go into that. So the final reflection is, I'm from a design department. So for me, very interesting was what started as a piece of speculative design, maybe a little bit whimsical, maybe a little bit fun, maybe not entirely serious, you could say, turned into a very interesting empirical study around the reactions to transparency, which informed a completely new research program around contestable AI. And that for me was a big surprise, but also a very nice surprise to see how a designerly approach might actually play an important role here. All right, thank you.
Thank you, Gert, for your talk and for telling us more about human-centered design and its relevance in the space of electric vehicle charging. The follow-up talk would come from my side, so I will have to do the honors of introducing myself. So my name is Gautam Ram, and I work as assistant professor in the area of developing control and components for charging of electric vehicles. More specifically, I focus on power electronics for charging, on smart charging, and integration of large amount of electric vehicles into the grid, and on battery modeling and aging, and we apply these concepts together for heavy-duty vehicle charging. So the topic of my talk would be on vehicle-to-grid, and more focusing on the technology trends that we are currently seeing, and what are the challenges that we are having in this space. So if all of you are not familiar with the phrase vehicle-to-grid, the phrase itself should tell you what it is. So we try to use the battery of electric vehicles as a means of energy storage for the grid. So to put that in numbers, you have a battery which is somewhere between 40 to 60 kilowatt hour of size, which can typically be charged in a slow charger at about 20 kilowatts, and in a fast charger, it can go up to 300 or 350 kilowatts of charging power. There was a question earlier in the talk from Jalal, and that question was, how do these different markets and ancillary services evolve? To put that in numbers for the Netherlands, typically vehicle-to-grid chargers are about 10 kilowatts. We have about 7 million cars here. That means you have 70 gigawatt of power capacity. To put that in context, the FCR market in the Netherlands is only 100 megawatts. So in other words, you have 70 gigawatts of supply, and you have 100 megawatts of demand. So which means I can make a hypothesis here. Maybe the FCR market may not exist at all in the future, and maybe grid operators write a line that charge point operator must simply, out of goodwill, control the cars and help the stability of the grid. Another benefit that vehicle-to-grid has over other means of energy storage is that we as people have always owned vehicles for the sake of mobility. On the other hand, we have not owned a battery storage in our houses. So vehicles will exist for our mobility needs, and the fact that they can also double up as a storage gives one big benefit that vehicle-to-grid has over other forms of energy storage. But the question is this feasible? Where is the technology heading, and what are the main challenges that we're having in this space? So I'm going to highlight 8 technology trends. Maybe it's not completely comprehensive, but at least I thought these were some of the main trends that we're having in this space. The first trend is size. In the past, if you went to a vehicle-to-grid project and you saw the charger, it will be as tall as me and weigh about 250 kgs. And if you told a person, do you want to put this charger in your house? They would say, I don't want something as big as a refrigerator to do bidirectional charging. On the other hand, what you have today, if you look, for example, the chargers from Wallbox or that from OVO, they're so compact, more or less at the same power level, that they can fit inside my backpack, right? So we have had a big reduction in the size of these V2G chargers. The question is, why has this happened? In the past, these chargers used to have a low-frequency transformer, a 50 hertz transformer to provide the isolation. On the other hand, now we are moved, like the examples that Sebastian showed, into high-frequency isolation, so which means the size of this transformer is something as big as it can fit inside my palm, compared to the 50 hertz transformer, which inside this charger is something as big as this. So we have gone really small in these transformer size, but also we use soft switching topologies now, and we also use silicon carbide wide bandgap semiconductor devices, because of the efficiency has also gone up in these chargers, so they become really compact. So it's much more easier to tell people, put that charger somewhere in the corner of your garage than this very big refrigerator that we had in the past. So this is very useful and interesting from a perspective of the user. The second technology trend is, you can see that the energy from solar is direct current or DC, and the car battery is also DC, and the car battery can be a storage for solar. The obvious benefit is, if you remember my graph of emissions per kilowatt hour, if you use solar to charge the car and also use the storage, these emissions actually go down to 0. So you are driving around with 0 emissions even from the power plant. And of course, the obvious benefits of integrating solar and EV charging is that everything is on DC, the car can be a storage for the solar, and also there's an expectation that large-scale penetrations of EV and solar will affect the grid and create congestion. So if we can control these two smartly, we can actually use one to solve the problem of the other. So the technology trend here is how we can integrate solar and electric vehicle charging together. This idea is not completely new. For many years, you could buy a solar inverter, you can buy a standard AC charger, and you can basically charge one based on the other. And if you have a simple control mechanism of the PWM pulse on the control pilot, you can basically change the charging power as the solar generation is changing. But the obvious disadvantage of this is that these solar inverters convert the DC power into AC, and we are again converting AC power back into DC. So what we were working on at TU Delft is to create a kind of a DC-based system where the energy from the solar is directly transferred to the EV fully on DC. So how do we do that? So we have a single integrated solar EV charger, and in this, the energy from the solar and the EVs all exchange on DC. We also have an inverter, which is now made bidirectional. And also another important point of the inverter is, in the previous example, we needed one inverter in the EV charger and one inverter in the solar inverter, and now you need just one inverter for both. That means the system is much more compact, and it's also much more cheaper than having two separate entities. And by making this isolated DC-DC converter bidirectional, we can actually use the EV as an energy storage for the solar. And also, you can have different kinds of power flow, so you get the functionality of a solar inverter and the function of the EV charger and a functionality of energy storage all built into one single system. We're now having a follow-up of this idea, where we also add an extra battery storage. This is especially useful when the availability of the EV is not 24/7. For example, your EV is going to work and coming back, but you still want to store the solar energy at your home. And this was part of the PhD project of William, and William will be defending his PhD next week. So if you want to know more about it, you're very much welcome at the Aula to learn about this. Another extension of the project is what we are having in the FlexiNet initiative, where one of the challenges we are seeing is that more and more EV chargers are taking space out of the parking lot. So we thought the best EV charger is one that you cannot see. So what we want to do, we want to put this EV charger under the ground. And the idea was, how can we put high-power electronics underground and use the soil and other means to actually cool these electronics, because we still have some efficiency losses there. We actually have the workshop for the FlexiNet project also next week. That's quite a coincidence. So on Tuesday, if you want to know more about this idea, you're welcome to join us at the Green Village and know more about hybrid energy storage system and underground power electronics. The next technology trend, which is the fourth trend I want to highlight, is how we can combine vehicle to grid, but not with solar on rooftops, but solar actually on the vehicle. While Sono Motors and Lightyear are probably not doing very well from a financial perspective, the idea is still quite interesting, because we do have a roof. We can put about 1 kilowatt of solar on top. And yeah, the orientation is probably not ideal, and you want to park it outside of the tree which is there in the parking lot. But you can still make 2 to 4 kilowatt hours of energy using this on quite a sunny afternoon here in the Netherlands. And if you go back to my number, 1 kilowatt hour gives you 6 kilometers. You can drive about 25 kilometers on a summer day just with the solar energy produced from your car. To think about it, it's quite a good amount of energy that you can get for regular day-to-day driving. But the problem is, of course, I cannot bring the sunshine in winter and give enough thing, at least in the Netherlands. But for other places, it is still a very nice idea that is catching up with OEMs. So here with the Sono, the idea that they proposed was that we can have onboard solar, and the charger inside the car is actually made bidirectional, so you can also feed the energy back to the grid. This actually brings us to the next technology trend, that is about, do we do AC-based vehicle to grid or DC-based vehicle to grid? So in the very first slide, when I show you these big V2G chargers, one of the main problems is that that charger has to process the DC to AC power conversion, so which means it makes these chargers anywhere between 2,000 to 10,000 euros, which is kind of a starting hindrance for DC vehicle to grid. So with onboard V2G chargers, where there's a fantastic work happening here in Utrecht with V-Drive Solar and the partners there, the idea is that, in this case, the Renault Zoe, the onboard charger itself is bidirectional, so you don't need an additional few thousand euro charger to actually do V2G. One of the main technical challenges here is how can we make this charger in such a way that it can apply to the grid codes available in different parts of the world, in different countries, especially considering the vehicle is actually mobile and will be moving in different places. So the benefit of the onboard V2G charger is this whole extra added cost of a charger is gone, and you basically kind of get a free V2G charger when you buy your EV. So that gives a very big plus, and more OEMs are actually promised this for the future. The trend number 6 is, which is now getting extremely popular, is what I would call as vehicle to load, or V2L. In V2L, you do not provide this power back to the electricity grid, but you provide it to a load. I mean, it's not a completely new technology. In the simplest form, we had cigarette lighters in cars many, many years back. But just think of it as much larger power scale. You can get AC power, and you can actually do the load. So there could be practical applications, for example, powering a campsite using your car, or running a vacuum cleaner, or if any of you ever wanted to sit in the middle of the street and play a computer game, you can actually do it like the guy who's sitting on the right. So it opens up a lot of opportunities to do vehicle to load. One of the interesting extension of vehicle to load is what we'll call as vehicle to vehicle. I do not know how many places there would be where you have to charge another vehicle with one vehicle, but there are use cases. For example, you're going for camping or you're going for hiking and you have an e-bike or a mountain bike and you want to charge that using your big 60 kilowatt hour battery pack. So there are very interesting use cases. A very good example is what is proposed from the GMC Hummer. It has a 200 kilowatt hour battery, and you can actually get 6 kilowatts of power to basically power other loads. So imagine that's quite a lot of power coming from your EV for different applications. The trend number 7 is coming from the Ford F-150. So what Ford has proposed is that you can connect your Ford. You also have about 9 kilowatts of vehicle to load power to power different kinds of tools and do outdoor activities. But also, you can use the system from Delta by which your car can then be used to power your home when the grid is down. There's a very big demand for off-grid applications, for example, in the US market. So to be able to power your home using your car becomes very interesting. So for example, at TU Delft, we have a project, the Drive2X project. We'll learn more about it from Pedro. And one of the things we're doing there is we're trying to build a charger which is powered from so it's the extension of the previous idea. You have solar power, you have a local battery storage system, but then you can also use your car to create a local grid to be able to provide power. Now, this is very interesting, not only in the developed world, but also in the developing world, where you don't necessarily have a reliable grid yet, or even no grid. How do we go to electric mobility if there's no electricity grid or reliable grid? So this could be an enabling technology, not only in the developed world, but also in the developing world. So the last and final trend that I want to talk about is autonomous electric vehicles, or shared EVs. What you see here is not from a science fiction movie. It is actually what you will actually see with any Tesla car that you drive now. It is capable of, to a large extent, maneuver and move on its own. So what I'm thinking is, what if we combine the ability of a car to move on its own and its ability to store energy? It opens up a completely new opportunity that you can do energy storage on demand at any location that you want. So in this example, you can have a lot of offshore wind coming from the North Sea, and then I take that power, I drive it down from Groningen to Delft, and then I power the home. Of course, one might ask, will I really do a dedicated trip for that? So what we are now investigating in one of our cross-disciplinary PhD with Wageningen and Groningen is we're looking at the social, legal, and technical aspects. How can we realize a flexible energy community, let's say, for example, based in Delft, that people can drive, meet, and exchange energy using their EV as a means of energy transport, especially in a situation where the grid is partially congested. So I've spoken all about the nice things about V2G, but the reality is not that easy. Bidirectional chargers, there are a lot of challenges. The bidirectional chargers do cost money. There's a question about what happens to the battery degradation because of vehicle to grid. We have competition from stationary storage and challenges, for example, lack of incentives, issues with aggregation, standardization, and also with cyber security. So I hope that with all of our efforts, we can overcome many of these challenges and try to realize the potentials that V2G has to offer. So this brings an end to my talk. If you're more interested about electric mobility, we have a massive open online course on electric cars. A lot of you have followed this course, or a lot of you have contributed to the course. It's a free course where we focus on technology, business, and policy of electric vehicles. And you can see more videos, lectures of myself and many others from here explaining the different concepts about electric mobility. Thank you for your time. So the next talk we have is from David Shipworth. David Shipworth is a professor of energy and built environment from University College London. David does his research into energy demand, and that is strongly determined by choices and actions of people in the energy system, particularly in the provision of energy flexibility from distributed energy systems in the built environment. David's talk today will be about vehicle to grid and vehicle to home from an end user perspective. David, the floor is yours.
That's great, thank you. Now, see if we can drive this thing. There we can. Right, thank you very much, and thank you to Gautam for kind of perfectly segueing through into this, what is really a kind of brief think piece about how, from an end user perspective, there are clear distinctions between vehicle to grid and vehicle to home. And one of the things in putting this together I started to really think about is that a lot of this comes down to questions about control and risk allocation. And I think we need to think about those from the perspective of both policymakers and people who are trying to operate the grid, but also from the end user perspective. So I'll go through and talk about how these, what are in some cases a kind of arbitrary distinction as to where power flows from the battery of a car, actually can become quite powerful, particularly in edge cases. So to start with, I think we need to talk a bit about this question of control. Now, one of the challenges, and I think we saw this in the first keynote speak from Jalal, there are a range of tools in the policymaker's toolkit about thinking about how we control power flows that come from distributed energy resources. One of the things that I'm concerned about, because one of the hats I wear is working through the International Energy Agency with a lot of government colleagues, including in the Netherlands, is we are not at this stage having a sensible policy debate about how we should allocate control within the system. And broadly speaking, I think there are kind of 4 places and ways we can allocate control. And this ties into thinking about electric vehicles and their roles as distributed energy resources. So the first of these is to think about direct power systems control. So I think that traditionally we've thought that this would be something that would dissuade users from allowing their vehicles to participate in the grid. So the idea is we hand the capacity for direct control to distribution system operators. In the context of buildings where these vehicles will be plugged into, of course we regularly have building regulations which stipulate what we can and cannot do with electrical loads in the buildings, and we're very happy to regulate how loads are used through building regulations, particularly around health and safety. So there's a valid question for policymakers as, if we move to a situation where we're reliant on the power in vehicle batteries to maintain grid stability, then that becomes a health and safety issue, the maintenance and continued operation of the grid. So I think there's a strong case for arguing that a percentage of control of vehicle batteries should be mandated and allocated directly under the control of distributed network operators. Now, we're not having that debate at the moment, but I think we need a debate in that area. The next level of control comes to contractual control, and this is where you get original equipment manufacturers. If I buy a product, say I buy an electric vehicle, then it could be a condition of that contract with the original equipment manufacturer that they can control a certain percentage of power in the battery. That has strengths and weaknesses. It's not as good, it's not as firm in terms of control as direct power systems control. It introduces a new actor, an original equipment manufacturer in there. It constructs risks for them. It has benefits for consumers in that it's much more an act of informed consent. So it's not a mandated control from government, but it's informed consent, and I can sign up or sign or not. But that's the next level of control. We then move into what we've heard a lot of this morning about market-based mechanisms. Now, there is a lot of focus on that, and I think a lot of thinking that has gone into how do we get the price signals right to incentivize people to allow their battery to participate in providing load into the network. This has advantages. I think basically it is great for price discovery, it's great for economic efficiency. I question how firm that load is because people's utility can change very rapidly, and we'll talk about this in the context of thinking about vehicle-to-grid and vehicle-to-home. So I worry in market mechanisms about what I think of as flexibility market defection, where people choose to basically not honor their commitments into the market because circumstances have changed. And that could be at a time when we most need power into the system. And then finally, we get into mechanisms around voluntary support of the grid. This is a model that Tesla used in the States, where you can allow your Tesla Powerwall or your vehicle to participate for the wider benefit of society. So each of these, I think, is part of a mix of how we should think about where control resides. Each has different levels of attractiveness to policymakers, through to distribution system operators, to original equipment manufacturers, and to vehicle owners. So it will ultimately be a balance, but we're not having a good policy debate about that at the moment. Now, in the context of vehicle-to-grid versus vehicle-to-home, from a kind of end-user perspective, these are completely different concepts. So vehicle-to-grid is transactional. You want to use the energy in my vehicle. Okay, how much are you going to pay me? I don't have any emotional relationship with my distribution system operator or my energy provider. They simply need to pay me to reimburse me for, use of my vehicle. Vehicle-to-home is entirely different. So vehicle-to-home, we can see the Ford F-150 Lightning here with the Sunrun system that allows it to power a home. This is really engaging a completely different set of decision priorities and thinking processes. So homes are ultimately about shelter, about protection, about comfort, and financial decisions taken in a domestic environment are driven differently. So as a colleague of mine says, what's the payback period on a new kitchen? This is not a question we think about. And what value do you place on keeping your family and your loved ones safe? The economics of that are completely different to thinking about what we do when we're in a transactional relationship with the market. So this takes us through to thinking about vehicle-to-grid versus vehicle-to-home under different operating scenarios. So in this one, I think when we think about the normal conditions of the market, which is what I think most of us spend most of our time thinking about, then I think from a grid perspective, they're essentially the same. Power, energy is pumped out of my vehicle battery and it flows to the nearest source of load. So that's very useful. It's different from an end user perspective because if it's vehicle to home, it's usually something that you're paid for by deducting that off your bill at your standard variable tariff rate. If it's vehicle to grid, you're bidding into a different market mechanism. So there's potentially a bit of a price difference there depending on where the power flows. But it looks the same from the grid. When we start thinking about issues where the grid is constrained, then it changes slightly. It's still, this power is being injected presumably behind a grid constraint, so it will again flow to wherever the load is. But from a user perspective, you're likely to get paid more if you're injecting it to alleviate a grid constraint. But you may also be worried about power limitations to your home. So you might be in a brownout situation and you're starting to worry about, how long will this go on for? Will I be able to run my air conditioning system and heat pump? So the kind of concerns about risk change. We move to blackout and the entire thing changes entirely. Now, obviously, if you're going to have power to home in a blackout, you need some kind of grid forming inverter, so the costs go up. But from the grid view, all of a sudden you're into what in the UK we would talk about looking after people on your priority services register. So who are the people who are at risk of a power outlet, of a power outage? Do they have, basically medical devices which are essential to keep operating? The costs and logistics of dealing with that are different. And from a user point of view, all of a sudden you're flipped into questions of health and safety and comfort. So your utility has changed radically once you're in a blackout situation. Now that's quite interesting, and then if we start thinking about that finally, we can start thinking about, well, what are the concerns that vehicle-to-grid raises? And what if we were to place that in a user-centered perspective? So could we come up with almost a charter of rights for end users that says that we will respect your priorities when we are using your vehicle? So we will prioritize keeping sufficient charge in your electric vehicle. So in the event of an extreme case, say you're in a storm situation or a bushfire situation, you can escape that. After that, we will prioritize your home because we know you want to look after your friends and family. Then we will prioritize the local grid, so you're supporting your neighbors, and then it goes out to supporting others. So what does this do? Well, this is quite interesting because I think the consequence of that, if end users appreciated and accepted and trusted the grid to prioritize them in that order, they would be much less worried about flexibility market defection because they could participate in flexibility markets knowing that in extremis, they will still be able to prioritize their home and their car and their vehicle. So they wouldn't have to prematurely opt out of flexibility markets thinking they have to protect themselves against the grid drawing power out of their system. Again, it probably reduces the risk of grid defection, this concern of policymakers that people opt out completely because the risks of allowing and staying engaged in the grid are reduced because you will always have priority for your personal safety. I think it also engages those who are thinking about completely separating from the grid, so it allows them to re-engage in the debate about providing services on a transactional basis. It also promotes the bundling of products. So we see with the Ford F-150 Lightning, you get the Sunrun system. All of a sudden, you're looking at PV plus a home energy management system, potentially an additional battery plus your EV battery. Now, that's really interesting from the grid point of view because that could reduce the loss of basically needing to shed load in an emergency because you know people are safe and people can support their own loads. So the social risks of load shedding reduce in that. So I think if we think about some kind of charter of rights for people in terms of the prioritization, and if they can believe and trust that, then that might actually significantly enhance the level of engagement we get. And we know from the psychology of control that if you give users the control so they can override things and they can protect themselves, they very rarely exercise that right. But if you don't give them the control to protect their own interests, then they will not grant you control over their assets. So psychology becomes really important here. So I think something like a Bill of Rights could be a really interesting way of actually enhancing the available assets on the grid. Right. Thank you.
Thank you, David, about your talk. I feel now that the psychology of control must be added to my list of big problems with vehicle-to-grid because the user perspective is very important. We are dealing with people's cars, and we have to include that. So our next speaker is Assistant Professor Pedro Vergara. So Pedro is Assistant Professor in Smart Distribution Networks at TU Delft. His research focuses on developing models and algorithms for controlling, operating, and planning electrical distribution grids with high penetration of different energy sources. His talk today will be about smart EV charging at scale and robust.
Thank you.
Thank you.
Good morning. Yes, so if I build on top of the arguments that were presented before, and if the market conditions are correct, the technologies are also proper and are there correctly deployed, we have customers that actually would be willing to provide services, participate in the operation of the network, what we end up with? A big optimization problem, right? We will end up with a large number of electrical vehicles, large number of decision variables if we see them from the perspective of the mathematical problem, and we need to solve that. So we summarize this problem as charging at a scale, and the presentation that I bring today for you is mostly as an invitation. So I'm presenting for you two big research projects that several departments here at TU Delft are participating. I'm not presenting the results that we have so far, I'm presenting more the general idea, the general concept of this project, and extending this invitation for all of you, from your research perspective, from the experience from your institution, your companies, to approach us and help us to define, help us to shape the developments that we are aiming to expect to have at the end of this project. So, as I mentioned, smart charging at scale. I'm presenting here the Robust and the Drive2X project. We will go a little bit in detail, but first let me give you a little bit of context. So if we see the market of electrical vehicles in Europe, we were leading during this year, taking the lead as the world's largest electrical vehicle market. However, due to the COVID pandemic, we saw a decrease in this position, and actually now is China leading the market. What are we expecting within this market? A large number of electrical vehicles. And the expectation, I believe that Gautam gave a sort of estimation for the Netherlands, but the estimation worldwide is for, if we see for 2050, is having around 1,500 million of electrical vehicles on the streets, right? So why is this a concern? Because we actually, if we aggregate all the capacity from these electrical vehicles, we actually end up with a very large capacity available there that can support the operation of the electricity infrastructure. Of course, there are two possibilities for this phenomenon of large EV growth or large EV penetration in our infrastructure. So we can see this sort of process as a double-edged sword, in which if we enable, we do not prepare the infrastructure, we do not prepare the market, the consumers, and allow them to participate in the charging process, we will end up with an uncontrolled sort of vehicle-to-one charging, which is unidirectional, right? And of course, you are aware of all the burden that this large amount of energy that will be drawn from the network will possess on our infrastructure. This, of course, then becomes a liability and an extra burden for our electricity infrastructure, and which is a case already here in several cities in the Netherlands. But at the same time, we see an opportunity, right? We see the opportunity of, from the system perspective, optimize this operation, coordinate this operation of charging of electrical vehicles, and see how then these assets and these resources that are there available can provide then the flexibility needed, for example, to charge when there is a large PV generation, when wind is blowing, following the arguments and ideas that were already presented. So with that, how do we see it? We see actually charging as an opportunity. And that's the main idea of these two research projects that we at TU Delft have a very big role, and that's what I wanted to introduce to you. So we have the Drive2X project. So we have the Drive2X project, a European project that just started, in which we at TU Delft and PowerWeb is one of the leaders, partners here, with a big chunk of work, going from the battery modeling, battery characterization, towards the algorithms for doing battery dispatch, and the impact and coordination of this charging process with the electricity infrastructure. And we have also the Robust project. That's a Dutch project funded by RVO, in which the main concern is the balance between how much flexibility can be drawn from these electrical vehicles, or these resources that are there, and what is the perfect balance between the flexibility drawn from these resources, and when do we actually need to enforce the network, right? There is, of course, there should be a limit. Flexibility enables to maybe delay some investment, solving some congestion issues, but it's not the final solution. There should be a sweet point, a balance between how much we can take advantage of the energy that is stored in these resources, but at which point we need to actually do investment into the network in order to enable larger penetrations, right? A larger number of electrical vehicles. So the Drive to F project, very long name as all projects, but we are focusing on developing vehicle-to-grid edge, so vehicle-to-grid different technologies. We have several case studies. We have a very large consortium covering geographically Europe. We have a very strong Dutch team, so we are working together with TNO, of course, TU Delft, PRE, which is an electrical vehicle manufacturer that I saw that, Gauta, you also work with them. And we have the city of Amsterdam. What are we doing in this project? And I apologize to my TU Delft colleagues. I'm focused on what I'm doing in this project, but we are a very big team. We have a very big team here. So we focus, for one side, the electricity distribution and the power system analysis. So we have a large number of companies focusing on this. What is the impact of this mass penetration of these resources? But of course, data science, the social science behind enabling customers to participate in these different type of markets. How do you design these markets? The different type of markets, which type of services these markets can provide. So it's not only about the classical markets that already exist, but now we're talking about designing markets for these electrical vehicles to provide support to the distribution network, right? Solving congestion issues and not only balancing at the national level. So what is the main objective of the Drive to Edge project? We want to develop knowledge, tools, models, and technology to cope with the vehicle-to-grid's mass deployment for Europe. We are focusing on four main perspectives: flexibility, designing of the flexibility markets that are going to enable this provision of support services, the type of technologies that we need actually to enable these electrical vehicles to provide these services, how do we scale, and of course the social side or these technologies. This is sort of a summary, and it's very clear the information that I have here for you, but I just want to sort of highlight what we are focusing, especially for the case of Amsterdam. So Amsterdam is one of the demo of this project, and what we are focusing there is designing the interface. So if we imagine a large number of public electrical vehicles chargers throughout the city, so what we would like to imagine, and the city of Amsterdam is imagine, it's a platform that is going to enable to bring together the system operators, customers that probably would not like for an aggregator or a different or third party to manage their electrical vehicles, but they would like to do it themselves. So it's also opening the participation, right? It doesn't have to be only through a third party. I can also do it myself with my own conditions. So we imagine for the city of Amsterdam an open platform that is going to enable this communication, bringing together all these partners, and this is the DSO sort of interface that you see over here. That you see over here in the corner on these figures. Of course, this is a very big project. There are other concepts there, but then what we are imagining for Amsterdam is this platform, and this is a sort of draft, and once again, this is a welcome, it's an invitation for you also to provide us with idea. How do you envision this, right? If you would like to participate and support the operation, how do you envision the interface? How do you envision that we should treat your data, how the municipality should treat your data, still respecting the data law, but at the same time enabling the provision of these services. Now I want to introduce you the Robust project, which, as I mentioned, focus more on the electricity infrastructure and at the regional level and the balance between investment and flexibility. right? This is, as I mentioned, this is a Dutch project. We're working very closely with system operator Stedin and the city of Utrecht as our main case study, because the city of Utrecht is already reaching some congestion points due to electrical vehicles penetration. And the main concept behind the Robust project is, okay, we have, how do we organize all the possible solutions, possible approaches to solve these congestion problems that are being seen in the electricity infrastructure, right? Which of these solutions should have more priority? Do we need to enable the market? Would the market, a sort of flexibility market, will solve the problem of congestion? Or because the system operator is actually in charge of keeping the reliable operation of the infrastructure, do they have actually to enforce some operation mandates? So would they have to intervene? Of course, that would be the extreme case. So what we see over here, and what we try to design is this, this sort of organizing all these ideas that are there actually to realize the provision of flexibility. So we have direct interventions by the system operators to solve extreme cases of congestion, but the idea is that we design the market in such a way that flexibility, so electrical vehicles, that the market enable this provision of flexibility services. Of course, we talk about, I'm missing the questions there. Let me see if I go to the end. It might appear. No. But the questions that I have here is, we talk a lot about flexibility. So we talk about providing flexibility to the network, but what exactly flexibility means? How do we actually measure? Can we sum up one flexibility with two flexibility units? If I use flexibility now, do I have that flexibility available for in 1 hour, right? So we all sort of understand the concept behind flexibility, but when it comes to the market, how we actually start trading that concept. And that's what we're doing in this project, creating this taxonomy for flexibility, this definition of flexibility to imagine this market. And of course, we know that flexibility is the key, but with the case of electrical vehicles, the key is aggregation, right? And then we come with a more complex challenge. We have aggregation of small batteries, or energy capacities, which responds with a human sort of behavior, and we bring then this uncertainty into the availability of this energy into the problem. So we have several challenges here. How do we develop then an efficient and scalable approach that requires for us to provide these solutions and just rather than mere approximations? This, of course, is related then with the quality of the market. And of course, what if it doesn't work? At which point do we define that it doesn't work and that we need to actually invest in reinforcement of the electricity infrastructure? That's what we aim to answer with these questions. Just to highlight once again, this is an invitation. You have ideas, you have solutions in mind, just come to us. We have a large research team covering large number of challenges in this project. Yeah, and we're open to welcome your ideas and your possible solutions. Thank you very much.
Thank you, Pedro, for telling us about the Drive2X and the Robust project. Our next speaker is Jianing Dong. Jianing is assistant professor of electromechanics at the Delft University of Technology. His research is in the area of electromechanical energy conversion and wireless charging of electric vehicles. And the talk that Jianing will give us today is about highly efficient wireless charging of electric vehicles. Jianing, the floor is yours.
Thank you, Gordon. So it's my pleasure to present our research on wireless power transfer here. I would like to start my presentation with a question to you. Why we charge electric vehicles wirelessly if we can buy normal conductive chargers from the market? There's too many answers, sorry. One by one. No plug? No plug? No plug. So more convenient. And from aesthetic point of view, no obstacle in the landscape. And you? real-time charging, so you can charge while you're driving. Well, yes, it can enable many different scenarios. It can also bring many conveniences. I'm not going to give you the answer, but I will show you some research we have done, and probably you can answer yourself after my presentation. Well, being able to transfer power wirelessly has been a dream in human history. So we were always wanting to transfer power out of nowhere. That's our dream. That's why right after the electricity were largely utilized, wireless power transfer was already patented. So it was patented almost like 1.5 centuries ago by Nikola Tesla. Then during the 1970s, we know there was the oil crisis, so there was a boom in electrical vehicle technology. And at that time, unfortunately, we didn't have good batteries. So range anxiety was really a problem, even more severe than today. So they proposed to have some wireless power transfer technology like this. So charge the car while you're driving. Unfortunately, again, we didn't have good enough power electronics. So it wasn't realized in large scale in the end. So in the new century, so there are more advanced batteries and more advanced power electronics. So now it's time to implement this system and tackle these challenges. Well, if we look at the wireless power transfer technologies, we can classify them into two main streams. One is the near field one, the other one is the far field one. How to define them? Depending on the electromagnetic wavelength we are utilizing, if the wavelength is a lot larger than the transmission distance, we call it near field. Otherwise, if the distance is so long, it's like from Earth to the moon, it's much larger than the electromagnetic wave, then we have to study the wave itself, then we call it a far field. So apparently, if we want to charge an electric vehicle, the distance we are talking about is in the order of 10 centimeters. So that's why it's better to use the near field technology. And for the near field technology, we can rely either on electric field, so we use a bigger capacitor to charge the vehicle, or magnetic field, so we use a coupled coils, a pair of coupled coils. And out of these two, this coupled coil technology, or the magnetic field technology, is the most promising one because it has a higher power density and the voltage level involved is also reasonable. So that's why, for us, we focus on the inductive power transfer, the near field magnetic field technology. So it can enable different scenarios. For example, charging of electric vehicles. It could also be done undersea. For example, now we have drones to do the maintenance of undersea cables, and this can be charged not by the cable going from the sea surface to the seabed, but wireless charging station located on the seabed. This way, you can solve a lot of issues brought by that hanging cable from the sea surface to the seabed. Well, coming back to the electric vehicle charging, so the wireless power transfer or wireless charging can happen at a very small scale, also at a very large scale. For example, in the case of electric bike, we can have this wireless charger embedded in the kickstand. So this technology has been patented by TU Delft, and there is already a startup company called Tyler using the patent. So the idea is to have the magnetic coils embedded in the tile. So you can just put a tile in front of your house, and the e-bike can be charged by putting the kickstand on the tile. This has been commercialized in a few projects now. And the wireless charging can also be with a very large power. For example, we got this project supported by EU progresses. Inside this project, we are looking at the so-called opportunity charging concept. So we charge the bus when the passengers are hopping on and hopping off. We only charge it for like 30 seconds to 1 minute. After that, it drives to the next stop. By utilizing this technology and charge it for very short interval at very high power level, like 200 kilowatt, we are able to shrink the size of the battery. So by doing this, we can carry more passengers, we can, well, reduce the power consumption of the electric buses, and we can also, well, integrate this technology with the new renewables, like a solar inverter embedded in the bus stops. I will show you, well, some more examples, but before doing that, we can come back to the question, why charging wirelessly? Still, we don't have the answer, right? I haven't given you the answer. But you may doubt, well, conductive charging is like, you see, we have contact. Electrons can just move in between, right? But for wireless charging, we have a gap. Would it be efficient enough? So let's take a look at the topology of the wider charging solution. So the same architecture has been presented by Bob Gotham, also by my colleague Sebastian. So as you can see, for conductive charging, we also need the so-called isolation. And to make it compact, we often use high-frequency transformer as the isolation stage in between. So here it is, the high-frequency transformer. However, so that's why there is no direct contact. The direct contact happens here, but in between, there is still, well, an isolation. So we have two coils. For wireless charging, we just replace this high-frequency transformer with an air core transformer. So we still have a pair of coils. They are not linked together by magnetic core. They are only linked together by air. Of course, it will have some consequence. For example, because of the loosely coupling through the air, the power factor will be low. That is to say, the angle between the voltage and current is very large. So transfer the same amount of power, we need a lot of current and voltage. But this can be solved by adding the compensation stage. So by adding, for example, capacitive components, we can bring the power factor back to 1, and we can save some current and improve the efficiency. So the added stages as the compensation and the air core transformer. The rest would be similar to the wider charging technology. If we really compare these two topologies, you can see that if we have 99% efficiency of every stage here, for the wider one, well, we could achieve an overall efficiency from grid to battery of 96%. And in reality, we are almost close to that. We can do it at around 95%. And for wireless charging, if we manage to design this S-Link well, we could also reach the efficiency of around 95. So there's no significant difference in the efficiency. So efficiency is not a problem, but how to achieve efficiency is really a problem. So how to achieve that? Well, there are so many texts on these slides, because if we really want to touch this topic extensively, we need a complete course, maybe not one, but 2 complete courses, just to cover every models of different components and couple them together and run the entire closed loop optimization loop. So I'm not going to do that in detail, but the secret weapon we have is for power electronics and the chargers is that we have built every model for every component and fine-tune them, try to make them accurate, and run them together. So in the end, we achieve different prototypes showing that they can achieve very high efficiency. So the first example I show here is a 3.7 kilowatt inductive power transfer system. We choose 3.7 kilowatt because this is the power level regulated by some standards. And what's unique about this prototype is it can tolerate variation in parameter drift of both the load and the components we use. You can see that in the previous slides, we have so many components. We have inductive coils, we have capacitors, we have switches. All of them may have some drifts in parameter. It could be caused by the temperature rise, for example. Could also be caused by misalignment between coils. Nobody can just park the car perfectly. The coils might not be aligned well, right? So as a consequence, well, the load might change, the resonant frequency might also change. To solve this problem, we made this reconfigurable system with a switched capacitor. So we are not using a fixed compensation component. We use a switch, and we can regulate the equivalent capacitance seen by the coil so that the power factor is always perfect. By doing this, we can charge at very high efficiency. As you can see from DC to DC side, it's above 96% efficiency. The second prototype is a charger which can handle 2 different voltages. We know that for the mainstream electric cars, we have a DC bus voltage of 400 volts, but in the future, there might be more and more with 800 volts. In the long future, it could even be 1200 volts as the power of the electric vehicle is increasing. So interoperability would be a big issue. You couldn't say this coil is just designed for 400 volt electric car. If you are driving at 800, sorry, we are not charging you. So that's why we propose this solution. We have a current doubler and voltage doubler made by power electronic converters. And we have 2 sets of coils. And if we are charging at 400 watt, we can put them in parallel. Otherwise, we put them in series. And there are 2 concepts we tested so far. This one, the first one, it has 2 coils, one at the front, the other one at the rear part of the car. And the second one, we have physically attached coils, but they are magnetically decoupled. So you just have one package, and it can do either 400 or 800, depending which car you are driving. And this one is another high power one, 20 kilowatt. We achieved 97% efficiency at the rated point. I said at the rated point, 20 kilowatt. So you may say, well, you are able to achieve high efficiency at 20 kilowatt. How about 3 kilowatt? How about 1 kilowatt? So how can the efficiency be guaranteed at light power? Well, we can do that by doing some more sophisticated control. So here we have the so-called dual-sided control for the power converters of wireless power transfer. So we can guarantee that the so-called zero voltage switching is always happening inside of the power electronics. So you will get loss-free switching in the complete range. In this way, we can make sure the efficiency is always in the high region, even the power is as low as 1 kilowatt, as you can see here. But there are remaining challenges we are not able to solve, or we can only solve partially. For example, one is safety and foreign object. Well, the inductive power transfer works the same way as our induction oven. So if you put a Coca-Cola can on top of it, it will be cooked, right? And it can also cause fire. So to do this, we proposed some solutions like this. We can put some auxiliary coils to detect not only the foreign object, but also the car. So if the car is not coming, we are not powering the coil. If we detect any metallic object during the charging, we stop it immediately. However, it doesn't solve all the problem. How about the foreign object is not a can, it's a cat. It's a baby. So there's still limitations in this technology. We need, for example, some visible light to detect these living objects. So that's the limit we have now. And this is also beyond our expertise. Well, there are more challenges. The other one is the heavy-duty vehicle charging. For example, if we have these big trucks in the mining application, usually these trucks should be charged at a megawatt level, as Sebastian mentioned. However, in most mining applications, explosion proof would be a big problem because there will be some dust, and if you have sparks created by plugging the chargers, it will explode. So wireless charging could be a solution to that, but we will have more problems to solve. So the charging power is so large, how to shield the magnetic field so that telecommunication and humans are not affected by the field. So there are a lot of challenges to be solved on the way. But it does bring many advantages. For example, you will get rid of the catenary and pantograph, and it can also be made modular and also embedded on the road. So that's it for my part. Coming back to the question, are you able to answer it now? Hopefully it helps a bit. Thank you.
Thank you, Johning. Thank you, Johning, for your talk on wireless charging. I think the first mass-produced EV in recent times, the GM EV1, actually had a wireless charger as a default charging system, and they publicly claimed they did it because they thought people would be scared to charge their car when it's raining outdoors. So going back to the explosion part, I think it's a very important trait. So now we'll have a short session to take questions from the audience. We are a little bit running over time by about 10 minutes, so we will still keep 5 to 10 minutes for the questions. And during the lunch, you can, of course, meet the speakers, and you can discuss further about your points. For the other speakers.
There's 4.
Just pass it around depending on the question. So, questions from the audience. And if you have a specific question for one of the speakers, you can also state it that way. Yes?
I think I can speak loud enough. Thank you. Can you hear me? Yeah. I have a question about sustainability issue, especially when it comes to vehicle to home, like David mentioned. This application is preferably with big vehicles, right? Of F-150 Lightning is 2.5 tons vehicle. And in my understanding, an electric powered car which is that heavy is not really sustainable, in a sense of if we think of electrical vehicles forming a part of a mobility energy transition, we should all go to lighter vehicles, right, and not to big heavy trucks. So I want to understand, is it better to have a home battery without the vehicle component, or is the vehicle better in double use as a heavy vehicle and a battery storage for home?
Right, I'll see. Ah, yeah. I think we're about to get a feedback loop from the mics. Thank you, yes. I think this is a question between what is, if you like, kind of theoretically optimal and what is socially plausible or possible. And I think, you know, you can look at the American car market, and every time I'm there, I kind of cringe at the sheer scale of the vehicles they move around in. I think that I agree that I think it locks up a huge amount of natural resources. You know, you can look at the scale of both their homes and their vehicles, so it would be more resource efficient probably to run with a kind of hybrid plug-in electric vehicle and a standalone battery. But I don't think, looking at the kind of market and stakeholder interests and the direction the US is going, that that's going to be a viable business model. So we're seeing lots of people pile into the big electric truck market. And so from that point of view, I would kind of grit my teeth and take the socially plausible over the kind of environmentally, theoretically preferable option of the two.
Yes.
Yeah, thanks for the excellent session. My question is, I know most of the use cases we spoke about in the vehicle to grid was, you know, from a lens of a home or residential. My question is more from a commercial fleet perspective. So how do you think, you know, or what do you think could be the ways of solving a typical challenge where there may be, you know, if you look at the typical duck curve in the grid, most of the production is during the day, but that's also the time when the fleet, for example, a delivery fleet for e-commerce, right? Those would be out delivering. So what do you think would be a good approach to optimizing a mix between, a distributed energy resource as well as electric fleet?
My answer. So maybe to understand a little bit the questions, it is not. I don't think that it's about how we define one solution, one sort of fit-for-all solution, but it's how do we actually take advantage of the underlying dynamic of your own electrical vehicles fleet to support the network. So to give, for example, of the to go to your example of the dot curve. So when we have large PV generation, yes, there is an opportunity there more from, for example, from large number of electrical vehicles owned by residents, because these vehicles are either parked at work, right, or at home if you didn't live. From the logistic perspective, these vehicles are usually parked after work, right, after working hours. So then you have the complementary availability of these vehicles when these are usually the periods for high wind generation after sort of working time, after dinner, which is also the point of maximum consumption, the peak curve. So you see that depending on the different type of behavior, there are opportunities there that can be exploited to support the network. And also another difference between these residential and fleet electrical vehicles, fleet is in general the behavior, right? These delivery companies, usually it is sort of known their delivery routes that they will follow when these vehicles are going to be used. And on the other side, from residential electrical vehicles, you have the sort of uncertainty and stochastic component, which is a little bit more difficult if the system operator would like to rely on services provided by them. So we have both.
In our recent analysis about technology gaps in vehicle-to-grid, we actually identified that fleet-based V2G could be one of the first avenues where V2G would actually be very successful, because we don't have to deal with the psychology of control. It's a purely commercial, and fleet operators usually know in advance how their vehicle is going to be used the next day. And a very interesting example are school buses in the US. You're going to have 100, 200 kilowatt hours battery in these buses. They're going to drive for 1 hour in the morning and 1 hour in the evening. They're going to be available whole day. And you have school holidays, and they happen quite often. And that time, even those 2 trips don't have to be done. So you have in the order of megawatt hours of storage available throughout the US from the school fleet. So these would be the first avenues where we will see the entrance of vehicle-to-grid. Maybe we have time for one more question from the audience. Yes? Just maybe pass the mic.
So one of the issues is the depreciation that I will incur as the EV owner, and typically with the conventional cars, the mileage is the indication that how old the car is and what's the depreciation. So with electric cars, not only the mileage but also the how many cycles the battery has gone through, and all of these applications that you mentioned, they have consequences on the number of cycles. So I was wondering first, is there any rough estimate that each of these applications, what would be their effect if we use it on a daily basis? What would be the consequence on the life cycle of the batteries and the value of the electric vehicles? And if yes, that how that the consumers can be informed about it?
There's a very counterintuitive result in current literature about battery aging. There's a school of thought where additional cycles from vehicle to grid is actually worse for the battery, but at the same time, there's actually scientific research which has shown that it's even better for the battery to do vehicle to grid. And I think a lot of you might be wondering why. One of the reasons is that in these studies, what they considered is that they brought the state of charge of the battery to a low value, and we know from calendar aging lithium-ion cells that lower state of charge just reduces the calendar aging of the battery. So on one side, you increase the cycles, but on the other side, you actually reduce the calendar aging, and then if you leave the battery on an average at a lower state of charge, they found in these studies under specific circumstances that the aging was actually reduced. So we actually, as part of the Drive to X project, are actually going to go deeper into this to see when and for what applications can we actually get this. Is it a generalizable result or not? So it's actually an open topic of research that a lot of researchers are looking at. Is V2G bad for the battery or not? And if so, how much is this problem? Maybe other comments about the aging? Okay, so if not, thank you all for your time. Thank you all for contributing to the session. We have a small gift for all of you. Maybe a round of applause for our speakers for this session. It's time for some lunch, and yeah, you're welcome to go down to the foyer and have your lunch. Yeah, and after the lunch, we have 2 separate parallel sessions, and the one is a session on the LTR PN, and the other is on the session about the energy SHR. So after the I think you would have already chosen the session that you want to work with, so you can go to those rooms after the lunch.
Yeah, so learn to run power grid, stay here, and then the energy share will go to body and mind. So if you go downstairs, go to the foyer, and then cross this clean route, then in the office, that will bring you to body and mind. So if you have any questions, just let us know. For now, enjoying the lunch. Thank you.